Good day from ChemHelp ASAP. This video provides practice for assigning the configuration of stereocenters, R and S stereocenters in molecules. Check the video description to find links to printable copies of these problems and their solutions. There will be links during the video that will connect you to other relevant tutorial videos. R and S stereochemical configurations are determined through a set of rules called the Cahn-Ingold-Prelog rules. The steps on the screen are the ones I usually follow. So after you identify your stereocenter, after you're sure that you do have a stereocenter, you need to rank the groups on the chiral atom. This is typically a carbon atom, and ranking is based on the atomic number of the substituent. We then make sure that the lowest priority group is in the back position, or is the group with a hashed bond. Actually, having the low priority group either forward or back is fine. We'll see examples of both in these problems. Third, we draw a circle through the groups number 1 through number 3. If that circle is clockwise, then we have an R configuration at our stereocenter. If the circle is counterclockwise, then the stereocenter is S. Fantastic. To practice these rules, we'll look at 8 problems, all of which show molecules that are approved drugs. Here we go. Here is our first molecule. The chiral atom is this carbon right in the middle. This carbon is tetrahedral and has 4 different substituents. The fourth group is not shown, but it is a hydrogen. We know that hydrogen must be there because this carbon needs 4 bonds in order to be a neutral atom. With bonds to 4 other atoms, carbon is tetrahedral. Tetrahedral atoms are depicted with 2 bonds in the plane of the writing surface, 1 bond above, that's our wedged or bolded bond to oxygen, and 1 bond down. Since nothing is shown as being down, that group must be a hydrogen atom, which by the rules of line angle structures does not need to be shown. For our purposes, let's go ahead and put in that hydrogen. We'll show it down with a hashed bond. All 4 groups on our carbon atom are now clear. We assign our priorities. Oxygen has the highest atomic number, so that is number 1. Nitrogen is next as number 2. Carbon is third as number 3. And lastly, we have poor hydrogen, which is number 4. And note that the number 4 group is shown back. Perfect. We don't need to concern ourselves about that for this picture. Let's go ahead and draw our circle through 1, 2, and 3. There we go. That is a counterclockwise circle. So the stereochemical configuration, in this case, is S. This molecule is S-zolpiclone. It's also known as lunesta. S-zolpiclone, and as we said, this is sold under the trade name lunesta. It's used to treat insomnia. Like many single enantiomer drugs, part of the name indicates the stereochemistry or properties of the molecule. In this case, the ES at the beginning of the name indicates the S configuration of the carbon in the molecule. Here is our next example. Again, we have a chiral center right in the middle of the molecule. This is a carbon. This carbon has 4 groups attached to it. And again, the 4th group isn't shown. It's omitted. It's a hydrogen oriented back. So let's go ahead and rank our different groups. So our top priority group is going to be nitrogen. Now, the other 2 groups are a little harder to distinguish because 2 of them are carbons. Which carbon is better? Well, this carbon right here is a carbon that is attached to 3 hydrogens. This carbon is a carbon, and it is attached to another carbon. I'm going to put a big dot over that carbon, and it's also attached to 2 hydrogens. So these are 3 groups on our carbon. When we evaluate this carbon, we want to list those groups in their priority order. So we're going to list the carbon and then the 2 hydrogens. So when we look at these 2 carbons, one of those carbons is only attached to hydrogens, and the other carbon, the carbon on the top, has a carbon. So we see the best group the top carbon has is a carbon, and the best group the bottom carbon has is a hydrogen. The carbon wins, and so this particular carbon is number 2, and the methyl group gets to number 3, and of course hydrogen gets stuck with a 4. So then we go through our circle. That circle is counterclockwise, and so this is going to have the S configuration. This molecule is called dextroamphetamine. Let's try to spell it correctly. Dextroamphetamine. This is a stimulant, and it's used for conditions like ADHD. Attention Deficit Hyperactivity Disorder. So this is a molecule. It can be purchased as a single enantiomer, and that molecule has the S configuration. Note again the name says dextro at the front. That's not a sign that it has the S configuration, but it indicates that its rotation of plane polarized light, which is a property of molecules with stereocenters, is in the clockwise rotation. Note that the clockwise rotation is different from the rotation that we assign by Cahn-Ingold-Prelog rules to determine the stereochemical configuration. Problem number 3. Here's our molecule, and we can see our chiral carbon is right in the middle of the structure. Again, this is a chiral carbon, and again we have 4 bonds to this carbon. We haven't shown the 4th because it's to a hydrogen, and this has the back orientation. So let's go ahead and put that hydrogen in. So, as usual, we need to rank our groups. So, of the groups on this carbon, the oxygen, that is number 1. Now, to the left and right, we have 2 carbons, and we have to think about these 2 carbons. So, for this carbon, that carbon is a carbon that's attached to other carbons. It's attached to a carbon, and let's put a dot over that carbon. It's attached to another carbon, and let's put a dot on that carbon. And it also has a 4th bond. It has a double bond to the top carbon. Now, when we have double bonds, we have to call those phantom atoms. And so there is a 3rd bond to another carbon, but that carbon is duplicated down here. It has all the bonds, but one of the bonds is a double bond. We put the double bonds in parentheses. These are called phantom atoms. Sounds scary, but it's not. Okay, now there's a lot of work for that carbon. Let's now talk about this particular carbon. That is a carbon, and it is attached to a nitrogen, and it's also attached to 2 hydrogens. Now, when we compare these carbons, the carbon on the left, the best atom that it has is another carbon. The carbon on the right, the best atom it has is a nitrogen. Nitrogen is higher priority. Nitrogen carries the win, so the carbon to the right is number 2, and the carbon to the left is number 3. Now, you might look at carbon number 3 and say, hey, I think carbon number 3 is getting ripped off because it has all these carbons, and the carbon on the right has all these hydrogens. It doesn't matter. The nitrogen makes the right side carbon higher priority. The left side carbon only has other carbons, and it loses out. Fair or not, that's how Cahn-Ingold-Prelog rules work. Now, we can't forget our hydrogen. That is group number 4. Now the hydrogen is back. That's a good thing. We can assign our stereochemistry as drawn. We go 1 to 2 to 3. That circle is drawn in a clockwise rotation. So this is an R configuration stereocenter. This molecule is called levosalbutamol. This is a molecule that's used to treat asthma. Note that levo on the front, it doesn't tell us whether the molecule is going to be R or S, but it does tell us something about the physical properties of the molecule. Levo is an indication that this molecule rotates plane polarized light and places a counterclockwise rotation on plane polarized light. So these names will sometimes tell you the configuration, sometimes they'll tell you about the optical rotation properties. All right, question number 4. Again, we have our key chiral carbon right in the middle of the molecule. We need to draw in our 4 groups. We'll only see 3 on that carbon. The 4th group is a hydrogen. And note that this one's a little different. That hydrogen is going to be a wedged group, a bolded atom group, because the carbonyl carbon is positioned back. So now let's assign our priorities. Nitrogen is going to be 1. And let's look at this particular carbon on the carbonyl. That carbonyl, that carbon has a bond to an oxygen. It has another bond to an oxygen, but that's a double bond to the same oxygen. So this is a phantom atom. And that carbon is also bonded to a nitrogen. Now let's look at this particular carbon. This carbon is attached to this particular carbon, let's get it straight, is attached to a carbon and 2 hydrogens. Well, the bottom carbon wins. The carbonyl carbon wins, so the carbonyl carbon is number 2, and the top carbon is number 3, and of course hydrogen is number 4. Now this example is a little bit interesting because our 4 priority group is forward. Now if we have the low priority group in the forward or up or bolded position, we can assign the configuration, but whatever we assign, we're going to get the actual answer is the opposite. So we just got to keep that in mind. We have to reverse our answer. So let's go ahead and draw our circle 1 to 2 to 3. No problem. Note that we've drawn this in a clockwise rotation, so you'd think that this is R, but because our hydrogen, our low priority group, is coming forward, this is actually the S configuration. Now this molecule is called levobupivacaine, and it is used as a local anesthetic. And again, the name tells us a little bit about the configuration or properties. In this case, it's about the properties. It has the S configuration, but the levo indicates that it has a counterclockwise rotation to plane polarized light. So on the screen is our next molecule. Here is our key stereocenter. And we, again, only have 3 things drawn. So let's put in our 4th group, which will be back, and that's our hydrogen. Now let's take a look at the other groups on this central carbon. One is this particular carbon, and that carbon has 3 hydrogens attached to it. Over here, we have this carbon, and that carbon's part of an aromatic ring. There are 2 other carbons in the ring attached to that carbon, and then one of those bonds is a double bond, so we'll put in the phantom atom form of that carbon. And now we have this carbon, and this carbon is part of a carboxylic acid. It's attached to 2 oxygens. One of those is a double bond, so we'll count that oxygen twice as a phantom atom. And now we can assign our priorities. Now, while we have 3 carbons attached to our central carbon, they're very different carbons. The carbon with the oxygens is going to be the first one, then the carbon with the carbons is the second, and the carbon with the hydrogens is third, and of course poor hydrogen ends up being number 4. Now, since our low priority group, the hydrogen, is back, once we assign this rotation about this carbon, we're pretty much done. So that's 1 to 2 to 3. That is a counterclockwise rotation. Therefore, the configuration of this of this carbon is S, and this particular molecule is called dexibuprofen. This is a single enantiomer of ibuprofen, which is a common over-the-counter anti-inflammatory. Okay, this is a little bit larger structure, but of course it doesn't matter how big the structure is. We're just trying to assign one stereocenter, and that's this carbon right down here. So don't be distracted by this full structure because we're just looking at one little piece of it. Now, as we've seen in other examples, we need to fill in a hydrogen, which is on our stereocenter. And now let's focus in on prioritizing our groups. So the nitrogen is our top group. The other two groups that are on the carbon, aside from the hydrogen, are both carbon. So this is a carbon attached to 3 hydrogens. And this is a carbon attached to an oxygen and 2 hydrogens. That carbon is going to be higher in priority, so that's 2. There's 3. Hydrogens 4. 1 to 2 to 3. That has an S configuration. This particular molecule is called levofloxacin. Levofloxacin is an antibiotic, a really commonly used antibiotic, broad-spectrum antibiotic. Now this molecule is a bit interesting because it actually has 2 stereocenters. And what we're going to do is we're going to go ahead on this slide, we're going to assign the left-hand stereocenter, and then we'll clean up our picture and we'll come back and we'll do the right-hand stereocenter. So let's focus on this stereocenter. Let's put in our hydrogen as our 4th group. Now it's pretty clear that the oxygen is going to be the top priority group on our chiral carbon, but the others are not quite as clear cut. So this particular carbon, as we continue down the line, is attached to another carbon and 2 hydrogens. Okay, fair enough. And this carbon, also as we go down the line, is attached to a carbon and 2 hydrogens. Okay, well that's a tie. So when this happens, you have to continue going down the chain even further. So now this carbon is the same as that carbon. That carbon is attached to an oxygen, a carbon, and a hydrogen. This carbon is now this one. That one is attached to a nitrogen and 2 hydrogens. So now we have a difference. The oxygen beats out the nitrogen. So this side, the right-hand side, is carbon. That's group 2. That's 3. And of course, we don't have to worry about hydrogen. It's 4. Fortunately, the hydrogen's in the back. So we just have to look at our rotation. 1 to 2 to 3. And that configuration is an R. So now let's clean up our slide and try to do the other stereocenter in this molecule. Okay, that's much nicer. Now we have more space to work with. So again, let's fill in our 4th group, that hydrogen. So for our chiral carbon, that oxygen is going to be group number 1. Now let's look at this carbon. That carbon is attached to another carbon, a hydrogen, and a hydrogen. And again, just like the last one, we have a carbon that is also attached to a carbon and 2 hydrogens. So we need to go further down the chain to find a difference. For our left carbon, as we continue down the chain, now this carbon is now referring to that position, we are attached to an oxygen, a carbon, and a hydrogen as we continue down the line. Now, as we look at this carbon, now we're focused on the carbonyl. So that's attached to 2 real oxygens and a phantom atom oxygen, because one of those oxygens is doubly bound. Well, now the right-hand carbon is winning. So that's 1, 2, there's 3. The hydrogen's 4. Fortunately, it's back, so we can just go 1, 2, 3. And that is an R configuration for that stereocenter. The name of this molecule is atorvastatin. often sold under the name of Lipitor. This is a cholesterol drug, and it is marketed as a single enantiomer, and the two stereochemical configurations in the molecule are both R. Here is our last molecule, and right in the middle there's our key stereocenter. As always, we need to add any groups that aren't shown, like our hydrogen. This hydrogen is coming forward, and we're going to take that into account because that's going to be our low priority group, and we want that back, not forward. So, but we can handle that. That's not an issue. So let's go ahead and set our priorities. There is a carbon coming off our stereocenter. That carbon is attached to a nitrogen, another carbon in the ring, and then one of those is a double bond to that carbon. So that's going to be a phantom atom. Here's our other attached carbon. It's attached to two ring carbons, plus one of those is a double bond. So again, that's a phantom atom. For this carbon, as we continue down the chain, we hit another carbon, and then there are also two hydrogens there. So when we prioritize these, this nitrogen makes this bottom group the top group. The carbon in the benzene ring is number 2. That makes that number 3, and of course hydrogen is number 4. Now we can go ahead and set up our rotation 1 to 2 to 3, and that looks like it's a clockwise rotation. But since our low priority group is forward, we have to reverse that. So it's not R. This is actually going to be an S configuration on that stereocenter. This molecule is dex chlorphenyramine. This is a common decongestant that you encounter in a lot of cold and flu medications. Well, that was our last question. There are 8 quick problems on assigning chiral carbons, and all these chiral carbons are contained in approved pharmaceuticals. I hope you found this video helpful. Please subscribe, give a like, or leave a question or comment. Thank you for watching, and remember that links to these problem sets are in the video description. Take care.